Welcome everyone to our June seminar. My name is Sumit Roy. I'm an assistant professor research in the Department of Engineering at Durham University. This event is organized through the EPSRC Network Plus for decarbonization of heating and cooling, and is part of a series looking at the different challenges of decarbonizing our heating and cooling sectors and behaviors. This month, we are hosting two speakers to explore the challenges and strategies for the decarbonization of heating and cooling. Our second speaker is Professor Daniel Friedrich, who is the Chair of Energy Systems at Edinburgh University. He's an applied mathematician interested in developing and using mathematical models for real-world problems, particularly in energy sector. Professor Friedrich obtained his PhD in applied mathematics from the University of Southampton. He obtained a postgraduate diploma in science in mathematics from the University of Auckland, New Zealand. Today, he's going to talk about Integrate project, which looks at integrating seasonal thermal storage with multiple energy sources to decarbonize thermal energy. Over to you, Daniel.
Good afternoon. Thank you for the kind introduction, and thank you for the interesting talk from the previous speaker. I'm Daniel Friedrich. As I said, I'm the Chair of Energy Systems, and I'm the PI of the Integrate project, which is an acronym for Integrating Seasonal Thermal Storage with Multiple Energy Sources to Decarbonize Thermal Energy. Today, I will give a bit more of an overview. I won't go into as much detail as the previous speaker, but I will touch on the different aspects of the project, which brings together four groups from three universities, two groups from Edinburgh, one from Glasgow, one from Hull, and I will give a brief overview of the progress in each of the teams. I obviously know a bit more of the progress of my team here in engineering at the University of Edinburgh, but I'm happy to go into more detail any of them during the questions at the end of the talk. So just about the aims of the Integrate project. So we want to consider seasonal thermal energy storage or long-term thermal energy storage as an important and vital part of a future low, or hopefully zero or even negative carbon energy system. So we want to use this, and for this we want to investigate the interplay, the coordination, cooperation between energy storage, heating, cooling, waste heat sources, otherwise potentially curtailed wind energy, as well as regulation and market frameworks. And we're going to use this to design integrated seasonal thermal energy storage systems, which hopefully provide affordable, flexible, and reliable energy for the customers in a district heating network, but also provide flexibility services to the wider energy system. And I will go into detail why these become important. As I said, this is a collaboration between the University of Hull, Glasgow, and Edinburgh, as the projects here funded by the EPSRC, and we have a large cluster of industrial as well as international partners which join us in our advisory board and which provide us with data from their operations and with whom we closely collaborate. I mentioned system flexibility, and the question is, why do we need extra flexibility? Currently, the flexibility in the UK energy system, and this covers both electricity as well as heating, is given by the national gas system. So the national gas system, which is shown in the figure on the left, has a line pack of about up to 690 gigawatt hours. So it's basically we are over pressurizing the system at night to store more natural gas in the system for the morning peak. And this provides the backbone for fluctuations in demand as well as in renewable supply for the electricity system, as well as for the heating system, which is mainly driven by natural gas. And with the current development with the war in Ukraine and natural gas becoming very expensive, and obviously the changing climate or the climate emergency, we need to change away from natural gas heating. So we need to go to different systems which are based on renewables, which are often non-dispatchable. So by that, I mean, we can't just switch them on. So they depend on the renewable resource. And for this, we need more flexibility in the system. While we are more or less, particular in Scotland, where I'm based, there at a very much decarbonized electricity system, the heating system is arguably more complicated to decarbonize. The peaks, which is shown in the top diagram of the site, so the change in demand from 1 hour to the next, just before the morning peak, is about 7 times larger. So the difference in the electricity. And the peaks are actually 4 times higher for heat demand than for electricity demand. The other thing is we obviously have a very large seasonal variation. So we have lots of heating demand in winter. While electricity has a seasonal profile, it is not as strong as heating demand. And the final point is heating is distributed. Basically, we need to change systems in pretty much all houses through the UK. So heating is arguably a more difficult system, but heating can also offer opportunities. Seasonal thermal energy storage systems in Denmark have been built for less than €1 per installed kilowatt hour. We can compare this to battery storage, which is over 100 or several hundred euros or pounds per installed kilowatt hour. So we are about 2 orders of magnitude cheaper. Obviously, there are drawbacks. We are only going to heat. We're not going back to electricity. We're only using that energy to heat. So we are going to a lower quality energy source, but we are potentially much less capital costs for this. So I will give a bit of an overview of, so this is sort of the motivation which we were looking at. A high level overview, what we are doing in this project is given on this slide, where we show, we start with, we have a power dispatch model, which is done by Andrew Lydon, the postdoc in my team, where we are modeling the energy system of GB, and we match it against historic data, and then we are using the energy scenarios from National Grid, so the future energy scenarios, to see what are the different projections for the future. And already, particularly in Scotland, due to the constrained transmission grid boundary between Scotland and England, we have quite a lot of curtailed wind energy. For example, in Ayrshire, which is just south of Glasgow, there are a number of wind farms which are curtailed for 30% of the time they could operate. And they actually get paid for it. So we're basically paying, I think currently it's a few £100 million a year, but it's predicted to reach maybe $1 billion in the next 5 or 10 years, with all the offshore wind coming online in Scotland after the recent ScotWind auction. So the amount of curtailed energy is probably rising over the next couple of years as well. So, and as I said, they're currently paid for it. So the idea is that we are using otherwise curtailed energy, and we get it through a conventional large-scale heat pump or potentially a resistive heater. And then we store it in large-scale thermal energy storage systems. And on the right side, there are the 4 different large-scale storage systems, which are the tank, the pit storage, which is quite common in Denmark, but which requires quite a lot of sub or above surface space. So for the UK, we're probably looking more at the subsurface technologies, which are the 2 at the bottom. So one is borehole thermal energy storage, and the one on the right is aquifer storage. A 5th one, which is not shown here, is using abandoned mines, which naturally flood with water and can also be used for heat storage. So all these systems have been used previously. So there's quite a lot of aquifer systems in the Netherlands, pit storage in Scandinavian countries, borehole systems are throughout Europe, and there's some in Canada. And there's actually a mine system in the Netherlands as well. But all of them are usually used with reasonably predictable solar thermal energy. They basically charge in summer and discharge in winter. So we want to use slightly less predictable and not as seasonal curtailed wind energy, as well as industrial waste heat sources, which are unfortunately not shown on this diagram. I will add it for the next presentation, but I'll come to that later as well. So in this project, as it says in the title, and I repeated, interplay between the different teams is key. So my team at Edinburgh, we are looking at the whole system modeling. So we're sort of in the center of the project. Then we're working with the colleagues at the University of Hull who are looking at industrial heat recovery and cooling, because most of these district heating systems with large-term storage, which have been developed in Denmark and other countries, they are commercially successful if they have waste heat sources. So we are using heat which would otherwise be just dumped into the atmosphere. Then we have the team of Professor Gioia Falcone at the University of Glasgow, and they are looking at the geological thermal storage. So borehole, aquifer, and mine thermal storage. And then the team of Mark Winskill and Ronan Bolton at Social and Political Science here at the University of Edinburgh are looking at policy, markets, and regulation. We need to look at this because we need new business models. We need to regulate the subsurface, and we need to find ways to make that economically viable as well. So this is another thing where things fit together. This is showing a transist model, and you don't really need to pay too much attention on the diagram on the bottom left. This is a sort of a traditional seasonal thermal storage system which uses solar energy, and we're going to replace the solar energy with curtailed wind as well as waste energy. So it again shows that the social and political science, they're looking at how we can evolve the market to make use of the extra flexibility seasonal thermal storage offers, but also to look at what are the challenges because we have now multiple stakeholders. Traditionally, these systems would be operated by usually one entity, but now we might have the district heating entity, the seasonal storage one, and the waste heat provider, as well as the grid or the wind park provider, which run these systems. So we need to make sure everyone, so contractually everything is fine. The University of Hull is looking at to quantify and also grade the different waste heat potentials through the UK, and I will show a map later on which shows that. And then the University of Glasgow is looking at the steady state as well as at the transient, and the transient become quite important in this case because we potentially charge more often than just seasonal. We might just charge and discharge every week or every month. It will depend on the curtailment structure of this. And here in my team in Edinburgh, we will combine these in simplified models as well as in a transist model as shown as this to design actually case studies for a number of different representative cases for GB. Let us start with the work which is done at my team. So Andrew Lydon has been developing a transmission grid model. So this is on the right-hand side. It shows a simplified transmission model with, I think, is 23 nodes. And we are using Python power system analysis. And he has developed this for GB with data for Great Britain, which is trained on historical data. And then you can use different scenarios from the future energy scenarios, and you can basically from these simulate according to the scenario any of the scenarios at any of the years between now and 2050. Obviously, these are only predictions of the future. There's a lot of uncertainty, but these scenarios are the best way to go along to try to see what happens, what are the changes in the system over the next 30 or so years. The second thing we're doing, and this is a PhD student, Lukas Franken, who is looking at that, is to generate dynamic demand models. And with these, we're going to develop 3 representative case studies. So we're looking at a campus system. For this, we're going to use one of the campuses of the University of Edinburgh. We're using a suburban system. This is in collaboration with Perth and Kinross Council. We're looking at the new Perth West development. And for the urban case study, we look at Glasgow. These 3 case studies will cover quite a lot of the different types of district heating network as well as of space we have on the above surface. We are furthest along with the campus. It is because quite a lot of university campuses have already a district or small district heating system. So these are prime targets to install seasonal thermal storage. And so the student is using machine learning to develop demand profiles because we can use very, very computationally expensive building energy simulations, but we can't really use them in long-term or planning simulations. So for these, we need faster to evaluate models, and machine learning has been shown to develop quite good prediction models for heat demand. So the figure on the left is from a paper which was done by Si Chen, she was a PhD student between myself and Ji Bin from the University of Glasgow. So we are going to build on that, but we're also looking at bidirectional interaction between these. So usually it's just, these are your inputs, so temperature, occupancy profile, this is your heat demand. It doesn't include what happens if we use the heat capacity of the house to slightly increase it or decrease it to provide flexibility. So Lucas is going to integrate these into the machine learning models. And then he's using them to develop a control strategy for the seasonal thermal storage. And the control is quite critical, as we'll come to when we look at the subsurface, because while the subsurface thermal storage have benefits of being less space intensive, they are not as fast. So we need to control them better. So we need to have a control based on forecasting of weather, demand, and curtailed energy. So as I said, the campus models, so we have just developed the first one for the Easter Bush campus, where we developed an energy center model, which is based on the curtailed energy on the left, going through a heat pump, and then linking this to the heat demand with short-term storage. And we have some preliminary results, which we hopefully will publish quite soon with on this. Let's move on in the interest of time to the subsurface modeling. So this is done, as I said, by the team of the University of Glasgow, and they are pursuing an integrated approach. So I've plotted again the three large systems, but we're mainly looking at the middle one, which is borehole, and the aquifer one. So Joya's team, they're looking at geological models, they're doing groundwater heat transport models, as well as detailed numerical models of the boreholes and wells. So for the Easter Bush case study, they did one for the BTES. So BTES stands for the borehole thermal energy storage, where they have a detailed numerical model, which models it's a U-shaped heat exchanger, which is a closed system. And during the charging, we pump hot water through it, and it basically heats up the earth around the U-tube heat exchanger. And during discharging, we pump colder water through it to basically take out the heat out of the ground. And so they are developing these systems, which will then be linked to the whole energy systems developed in my team at Edinburgh. The second technology is the ATES, which is the aquifer thermal energy storage. And again, that's done by the team at Glasgow, where this is now an open system. So usually we have two boreholes. So we have in blue one here is the cold one and the hot one. So during the summer, we reject hot temperature, for example, from air conditioning units. So we heat up one part of the aquifer, and during the winter, we take this hotter temperature from the hot side and reject cold energy, the cold side. So ideally, we have a balance between heating and cooling, and this is what they quite a lot see in the Netherlands. Part of the project done by the University of Hull is the distribution of waste heat sources. And in the red, you can see their preliminary map of waste heat sources for the UK, which is, as expected, clustered around the cities and industrial centres. So we have London, Birmingham, the Manchester, Liverpool, then on the other side, the Newcastle, and then a bit in the central belt of Scotland. So there's quite good proximity to populations, which is good because district heating systems will usually be built at campuses and cities. So there's quite good overlap between the heat sources as well as the population centers. So there's quite good scope to integrate them together more and not waste this industrial heat, but put it to good use for heating of spaces and potentially hot water as well. So for the Glasgow urban case study, they have identified 12 heat sources, which are shown here with the red dots, just within, I think, 10 kilometers of the city center. And if we go even larger, then this number doubles. These heat sources, they're currently in the process of going through them. And here's a small sample shown with some of the exhaust temperatures. Obviously, the Tata Steel and Promat mineral products at 500 degrees, this is probably not the waste heat which is available, but will be reused inside the plant itself. But the other ones might potentially be available temperatures. So the Hull team is currently looking at these to not just look at the location and temperatures, but also of the quantity of the heat, as well as potentially the temporal distribution. So is this waste heat available over the whole year, or is it sort of a batch type process? So This is what they are currently quantifying. And finally, let's move on to the market regulation and policy framework, which is done by Ronan and Mark. So they are looking at technology innovation systems. And the first step is to see, okay, what have other people done? What did they do in the Netherlands and in Denmark where they have these systems? So they conducted interviews with actors there, and then they tried to relate these findings following the technological innovation systems framework to the UK. And I will briefly talk about the ones for the ATES in the Netherlands and the PTES, or the pit storage in Denmark. So the ATES, so the Netherlands has around 3,000 ATES systems, which is probably 90% of all the systems in the world. They have very good hydrogeology for that. In the UK, we still have good opportunity, maybe slightly less than in the Netherlands, but the hydrogeology is available, and there are maps of the aquifers which are under most of the population centers of GB. The other thing is the climate is slightly cooler here, but in the south of UK, we have growing cooling demands, particularly in London and the southeast of the country, southeast and southwest of the country. So the balancing of heating and cooling can work. The further north you go, we have less cooling demands, so ATES might not be the right solution as well. The other thing is ATES is a slightly lower temperature technology. So currently they are around 25 to 30 degrees, but there is work going on high temperature. But this requires slightly more energy efficient buildings, which the current UK stock is not as energy efficient as some of the Dutch buildings, but with the current regulations, there is good scope to do that. Now they're taking these findings and bringing them to UK market players to see how we can use this framework to learn from the Netherlands for the regulation in the UK. The second case study they're looking at is the pit thermal storage. So there's only quite small number, because these are basically giant lakes with a floating insulation on top, so they require quite a lot of space. So they're usually in rural areas or at the city boundaries. So in the densely populated UK, this is probably not the right solution, except in a few special cases. But it's still interesting to see how they have been incorporated in the district heating systems in Denmark. So usually they are linked to waste incineration as well as waste heat. So again, is this topic of you need to make it pay, you need to get reasonably cheap heat into these systems. Because similar to every energy storage technology, pit thermal energy storage and all the subsurface ones, they are losing you energy. So there's dissipation of heat into the ground in this case. So you don't get as much energy out as you put in. So the only thing to make them pay is by the flexibility they offer to the system. By using heat, electricity, or any other energy source which would otherwise be wasted or couldn't be used, and then shifting it in time to a period where it is more valuable. And so this could be waste incineration, solar thermal in the summer, or hopefully curtail wind energy in the UK. So from this, the team of Mark and Rona are trying to learn and try to again speak to UK stakeholders to come up with guidelines for policy regulators as well as industry. With this, I would like to conclude. So just as I said, heating, cooling is very challenging, but there's opportunities due to the reasonably low cost compared to battery storage and other storage technologies, cheap form of storage. To get to these benefits, we need to integrate different energy sources. So we need to have low cost heat to charge these systems, because seasonal thermal energy storage, as I just said, loses energy, but it can provide flexibility to the system. And this flexibility is critical as we go forward and remove more and more natural gas-driven systems from our wider energy system. The first results of this project have been presented at conferences, and we have an upcoming review article and some other things coming out. So hopefully we can update this network as we go along into the future. More deliverables have been achieved from this project. Thank you very much, and I'm very happy to take any questions now.